Okay, welcome everyone to this CDAC webinar, the 140th webinar in our series on materials in extreme environments. Today, it's my great pleasure to introduce Adam Jaffe from the University of Notre Dame. Adam received his bachelor's in chemistry from Princeton University, followed by a PhD in inorganic chemistry from Stanford. There he worked with Professor Karuna Dasa, as well as Wendy Mao, former CDAC partner, exploring optical and electronic properties of hybrid inorganic and organic materials, including their energy storage, light emission, and compression-induced behavior. Adam joined the lab of Professor Long at UC Berkeley as an NIH fellow, where he studied separation of O2 from air and redox active porous materials. He then started his independent research program at the University of Notre Dame in 2021 as an assistant professor. And there his group explores, develops new hybrid material platforms to target energy-related challenges and examines their structure-property relations, including their high-pressure behavior, which I hope you'll tell us about today. Over to you.
Well, thank you so much for the kind introduction, and thank you. I'm really honored to be able to deliver this 140th CDAC webinar, and being honored to be invited. And it's really a pleasure to get to talk about the science going on in the Jaffe group here at Notre Dame with all of you. And I really look forward to everybody's questions and feedback. So let me switch over to sharing my screen. Moment. Okay. And so I believe here now I have, okay, everything's working. Hopefully everybody can see my screen as well as my laser pointer here.
Excellent.
Okay. Today I'd love to tell you a couple different vignettes, both about a new class of compounds that we're really trying to develop and understand called hybrid bronzes. These are mixed valence organic inorganic metal oxides. And so the first stories I'll tell you are just to orient you about this class of compounds that's perhaps underexplored. And then the major story of today's talk will be how they have some very interesting emergent behavior under pressure. I first like to start by thanking my group and the folks who really did the work. Those highlighted in bold in this column are graduate and undergraduate students who did the science that I'll talk mostly about today, though the ones who are not in bold have also been contributing a lot to the group in other project areas. We're also really grateful to a range of different excellent collaborators, both those at Notre Dame. So that's Professor Alan Oliver, our crystallographer, Professor Theda Chen, who's done some density functional theory calculations with us, Professor Evgeny Kovrigin, who's a NMR specialist and research professor, and Professor Mi-Jun Lee, who's helped us with mass spec data. And then I'm also very grateful to Doctors Bianca Haberl and Matt Tucker at Oak Ridge National Lab, who've helped us both with some Paris-Edinburgh cell compression of our materials, as well as and then analysis of some scattering data from neutron measurements. We're of course really grateful to be able to access these wonderful facilities at Argonne National Lab, Oak Ridge, and Berkeley. And I'm also really grateful to both Notre Dame for some funding, but especially the NSF Career for funding a lot of this work. Okay, so I don't think I have to belabor the point that materials chemistry and materials science is really synonymous with human development. Even early on in our history, we developed the use of metallurgy to extract ores, things that maybe were chemically inert, like gold, and make jewelry from it. But soon after, of course, developed copper and even bronze and early alloy, not necessarily too related to the bronzes I'll tell you about today, and you'll see why. But also we take use of naturally occurring polymers like lignin and cellulose, as well as now more kind of synthetic polymers that are in our everyday life. And so ultimately, all of these developments in materials science and materials chemistry have enabled a better quality of life and the scientific and technological advancement of society, and allowed us to meet some important challenges, including energy capture in the form of solar cells, energy storage in the form of batteries, energy utilization that's perhaps more efficient than Carnot efficiency in the form of fuel cells, and information processing, which itself is also very energy intensive, requires materials to meet these challenges. Ultimately, the reason extended solids, materials with infinite bonding in one or more directions, are important is because that chaining together of orbitals, which of course Roald Hoffman covered at length in his famous small novel, Solids and Surfaces, which I highly recommend, that gives rise to electronic bands and an electronic structure that then gives unique optical properties to many solids and further allows for things like electron transport, so the movement of charge over long distances. But also extended solids, as we know, have surfaces. Unlike a molecule, which is an isolated unit, a solid, its particles, can have surfaces on which interesting chemistry can occur, things like catalysis, which is hugely relevant to our modern day life. And also this extended chaining together of orbitals give rise to important magnetism and other collective phenomena, which I think in the high pressure community, we're of course very familiar with how high pressure is often necessary in order to explore things like superconductivity. So ultimately, I would argue that the extended physical and therefore electronic structure of solid state materials and their stability are huge benefits that really enable their use in many different applications. But though I love solid state synthesis, I would argue that these syntheses are relatively energy intensive, so many hundreds of degrees Celsius. And furthermore, during those syntheses, it's relatively difficult to tune the outcome of that reaction. On the other hand, molecular chemists are capable of exquisite synthetic control, so the precise tuning of molecular architectures. And in general, these compounds are easier to process, meaning we can synthesize them at milder temperature, often in solution. On the other hand, however, they might lack some of the durability necessary to, for example, last in a solar panel for 20 or 30 years on your roof. And because they're isolated units, they lack these extended electronic structures. And so my group and I are hybrid material chemists, and we really like thinking about how can we put together molecular species and solid state materials and get the best of both worlds. But we really care about figuring out what makes them tick. In other words, how can we understand their structure, property, composition relationships? And as I think I don't have to really convince anyone in this audience, high pressure is a really great way to do that. Briefly, I did want to highlight one area going on in our group that I think it would be really interesting, especially to examine under high pressure. And that's the idea of using reagents such as those shown on this slide to synthesize or modify solid state materials. So if we want to develop more synthetic control, we might want to be able to install specific atomic units like those shown in red here, these nitrogen, oxygen, or sulfur atoms, for example. Molecular chemists, Dick Holm, Keith Wu, and many other luminaries in the field of organometallic and organic chemistry have used these molecular reagents to great effect to synthesize molecular species where each of these molecules have internal driving forces to transfer or exchange atoms. So one example is azide here, N3 minus. If we break this N-N bond, we form then a nitrogen bond to our substrate, as well as a nitrogen-nitrogen triple bond, and that's highly enthalpically favorable. But we've also evolved a gas, which is entropically favorable. Other compounds like Lawson's reagent, shown here, are capable of swapping out sulfur for oxygen, driven by a strong phosphorus-oxygen bond formation. Or pyridine N oxides, such as that shown here, can break this NO bond and formally oxidize some molecular substrate or some material, then transferring an oxygen atom. And so we believe there's some room for exploration here to use these molecular reagents to install either dopant atoms to coat surfaces of particles, or even topotactically exchange atoms throughout an entire structure while retaining its ultimate architecture. And so you might imagine doing this in one of two ways. One would be start with your atom transfer reagent of interest, where this is your atom you're transferring, shown in pink, and a carrier molecule. And if under the right conditions, you can combine it with some linkers as well as other metal ions, perhaps you can self-assemble a hybrid material in bulk. That then you can apply a stimulus when desired, such as light or heat, or perhaps even pressure, in other words, stress, to then break that bond from the carrier portion of the molecule, driving us to a new or at least difficult to access solid. Alternatively, you could imagine simply having this reaction occur in an exchange type fashion, a metathesis, a molecular chemist might call it, or a topotactic bulk exchange. And so our group is certainly actively working on this. We've made some 2D metal thiocyanate materials that have pyridine N oxide ligands, where that oxygen atom is bound to the metal centers. And we're excited to figure out how more to play around with these systems, tuning the reduction potentials, that NO bond strength, and ultimately understanding more about their optical and electronic properties to ultimately induce some of this atom transfer. And we're exploring these under pressure as well, though I won't tell you about that today. We've also discovered a new bismuth oxyazide. And so many of you may be familiar with these layered bismuth oxyhalide compounds that have the formula BiOX that are layered compounds where the halides are in these apical positions. And it's possible through exchange chemistry to exchange those for other halides. And we chose to exchange it even for pseudohalides such as azide and have now seen some thermolytic cleavage of those azides to make a putative bismuth oxynitride. And so we're excited to also explore that under pressure. And finally, we've also installed pyridine N oxide units in these layered metal cyanide materials called Hofmann clathrates. These are essentially two-dimensional analogs of Prussian blue, the three-dimensional iron cyanide framework, where here on these green atoms, which in this case are iron, though we can also install nickel atoms there, we've installed neutral pyridine N oxide ligands that we've then shown we can break the NO bond for, driving off O2 as well as oxidizing some of our organics and giving rise to then the layered iron pyridine compound. And what's kind of neat about this system is that this chemistry only occurs in the iron congener, whereas if we install nickel at that same metal site, this reactivity does not occur. So I just wanted to highlight some other chemistry going on in the Jaffe group, and especially point to, I think, what are some real opportunities to explore that chemistry also under extreme conditions. The main story of today is to talk about hybrid bronzes. And so our group, again, seeks to combine the best of both worlds from molecular chemistry and materials chemistry. And to build a new hybrid material platform, we sought to establish what would a good promising inorganic parent compound be that has the optical and electronic and other physical properties that we might want to then engender within our hybrid system. And we got very interested in metal oxide bronzes. Some of you might be familiar with this, but others might be a bit confused by the name bronze. The only similarity between these metal oxide bronzes and the bronze alloy of Bronze Age fame, which is a copper tin alloy, the only similarity is that they are both shiny. And so the metallic luster of these metal oxide bronzes comes from the fact that they are mixed valence oxides of the form AXMOY, where taking a molybdenum, tungsten, vanadium, or niobium oxide and reducing it by n electrons, either chemically or electrochemically, and then inserting cations for charge balance, or alternatively having oxygen vacancies for charge balance, we get a mixed valence compound, and those electrons are relatively delocalized. And that sea of relatively delocalized electrons gives rise to a metallic luster that even back in the 1800s, Friedrich Wöhler recognized as looking a lot like a bronze, hence the name. The cations we typically intercalate for charge balance are protons or other alkali cations. And so for the remainder of my talk, I'll be talking exclusively about compounds into which we've intercalated protons, which does present some challenges. And so actually, I think I see Malcolm Guthrie on the call with whom we're collaborating and trying to figure out where exactly are these protons. So metal oxide bronzes are really interesting compounds because, for example, now looking at this plot, for sodium tungsten oxide, so NaXWO3, as a function of sodium concentration, which is a proxy for its level of reduction, it goes through a range of really beautiful color changes. So it is electrochromic, and hence it's actually used in smart windows. And that's due to all of these series of structural changes going from a low to a high symmetry, and the introduction of new electrons into these formerly empty states. And that actually causes the compound to transition from a semiconducting or non-metallic state, in which conduction of electrons is an activated process, to a metallic state in which it's then a non-activated process. In other words, there's no real barrier to movement of those electrons. In fact, many of these oxide bronzes are even superconductors, and they've been studied for decades for their variable light absorption properties, their tunable conductivity, which is even important in charge transport layers in devices, their catalytic activity, and a range of other very interesting physical and electronic behaviors. And so as hybrid material chemists, we view them as really ripe for further enhancement. For example, installing new methods to tune their structure and chemical functionality by installing molecular species, perhaps stabilizing some of their more reduced phases, and even incorporating molecular handles. So for instance, spectroscopic reporters that could give us more insight into their electronic and vibrational behavior. So the pitch is this: to make hybrid bronzes that have mixed valence metal oxide layers, templated by ordered arrays of organic molecules, where here these different colored spheres are supposed to represent different functional groups you might imagine incorporating in these molecular layers. And the hope would then to be install new molecular reactivity and structure directing behavior, but maintain the mixed valence properties and all of the optical and electronic behaviors that come with that of the metal oxide layers. I would argue that then to develop such a platform, understanding how those molecular interactions dictate and affect charge transport, and in general, how charge transport behaves within the metal oxide layers would be one important characteristic to understand. And it would also be very interesting to be able to induce charge transfer, perhaps by light or driven by potential or by pressure between the metal oxide layers and the molecular species or vice versa. And ultimately, if we do understand more about those potential processes, we might be able to develop design principles for future applications. To build the platform, we came up with two different major strategies. One was a self-assembly process, where under the right conditions, given our molecular species and either a metal oxide or polyoxometallate precursor, you might imagine being able to self-assemble these into a fully oxidized hybrid metal oxide. So we still don't have our mixed valence, and it's hence not a bronze yet. But then upon reduction, we could get the mixed valence hybrid bronze state. We're certainly not the first people to make organic templated metal oxides. The folks highlighted on this slide are some of the kind of big players in the field who've really made major contributions that have extended inorganic structures. And what I mean by that is extended metal oxygen bonding, which gives rise to actual band-like band structures where we have a valence band comprised of oxygen 2p orbitals and a conduction band comprised predominantly of metal d orbitals. But what I think is still underexplored is the optical and electronic properties of these compounds, the control of mixed valence, and therefore control of things like charge transport. And finally, also the ability to install molecular species that are perhaps one might say interesting, things that have redox activity, photoactivity, or reactivity. And further understanding then in this now more multivariate system where we have more tuning knobs for both structure and property, how can we control and understand the behaviors? I would say another strategy would be to start with a layered metal oxide. This is actually the crystal structure of molybdenum trioxide, and first reduce it either chemically or electrochemically to get the inorganic molybdenum bronze, and then intercalate organic molecules of interest, perhaps driven by Lewis acid, Lewis base interactions. And Schulhorn and Steinhoff did examine this back in the 1980s and actually found that hydrogen molybdenum oxide is capable of intercalating a wide range of neutral organic bases such as pyridine. However, we tend to favor this first strategy, the self-assembly strategy, because it allows us to understand the atomic level structure of our compounds because we can derive single crystal structures. So all the folks on this slide have been able to really help build out this platform where we've been able to incorporate vanadium, tungsten, and molybdenum in a range of different hybrid layered structures that incorporate many different organic molecules of interest. These are synthesized under hydrothermal conditions, so we combine organic precursors, either a metal oxide or a polyoxometallate, in water in the presence of air, seal it in a steel pressure vessel, and heat it up just above the boiling point of water, and that gives rise to single crystals, which is generally a relatively mild synthesis. And so that's enabled us to rapidly build out this platform. But actually, what some of my students found is that we can even synthesize these compounds on gram scale simply by stirring the precursors together in water at mild temperatures in the range of 60 to 80 degrees Celsius. So literally stirring things in a vial on a hot plate gets us a really good match in terms of the phase identification shown here in these powder X-ray diffraction patterns for both the molybdenum and tungsten congeners. Here I'm just showing a few examples, comparing the powder patterns from both solvothermally synthesized compound and those synthesized through stirring, and we see that we get very good match between those. And what that means is if we already have many different single crystal structures where we have precise atomic positions, that really enables Rietveld-based refinement of structures where we perhaps get a high-quality powder pattern but aren't able to get a single crystal structure, and maybe where we've only swapped out one functional group or something like that. These compounds are also quite stable. So this is, for example, the 4,4' bipyridine templated hydrogen molybdenum oxide or hybrid bronze. And when we submerge this compound in water in the presence of air for over a month, we see relatively no change in its powder pattern and no evidence of any of its dissolution into that water solution. So these are quite stable compounds as well, and thermogravimetric analysis says they're stable up to even about 300 degrees Celsius. So the first stories I'd like to tell you about are a little more about why we're studying these compounds, though of course, because this is a high pressure seminar, the bulk then of the rest of my talk will be about their high pressure properties. The stories I'd like to tell you mostly about are about their charge transport and how structural templating factors affect it. And I think that will then translate nicely into their high pressure behavior. The hybrid vanadium bronzes, we synthesize using V2O5, vanadium pentoxide, as a precursor, which itself has a layered structure with these vanadium oxide pyramidal units that either are corner sharing or edge sharing, depending on which direction you're looking. Combining these with organic amines, such as this ethylene dioxybis ethylamine, allows us to break these metal oxygen bonds and reform a new structure that might at first look similar, though a little bit corrugated, but I assure you, and I'll kind of convince you of this in a moment, that bonds have broken and reformed. Actually, many of these amines are sufficiently reducing under these conditions to reduce some of the metal oxide centers, and then others are protonated and incorporated for charge balance. So I don't view this as an intercalation, but rather a templation type behavior because we've broken and reformed bonds and then inserted the ammonium species, which then have both hydrogen bonding interactions with the metal oxide layers as well as with each other, but are also present for charge balance for these anionic metal oxide layers. But because we have all of these now very clear intermolecular interactions and molecular interactions with the metal oxide layers, this enabled us to hypothesize that we should be able to come up with a series of different molecular units that should template different structures and actually might ultimately give rise to our ability to look at structural features as a function of pressure relative to things like chemical pressure, though that won't be the subject of my talk. So here's the series that we came up with that have either higher or lower charge density. In other words, how spread out or localized is their positive charge. But also, these are primary ammonium species and therefore can hydrogen bond, whereas quaternary ammonium species cannot. And the quaternary ammonium species here, this methyl and ethyl viologen, also have larger steric profiles. When he crystallized compounds based on those molecules together with vanadium oxide, Suchen found that even given 8 ligands, we got 9 different structures. In one case, depending on pH, actually, this N-methyl ethylene diammonium species could come along with a structural water, and therefore we got 9 different structures with a range of different architectures. To highlight how those architectures are different, the vanadium oxide layers can either come in a stoichiometry of V8O20, where here we have an up-up, down-down motif, or an up-down, up-down motif. Both have the same stoichiometry, and other than that are very similar in that they are corner sharing along one direction from a top-down view, but edge sharing along the other in these ribbons. However, it's also possible to engender V6O14 2- stoichiometry or V4O10 2-. And here we've now introduced a new coordination geometry, these vanadium oxide tetrahedra. In one case, we have dimers then of square pyramids, and in the other, these more corrugated ribbons. And the reason that I'm highlighting these vanadium oxide tetrahedral units is that if we consider them by themselves, they are poor hopping sites for an electron. I'm not actually aware of any crystallographically characterized vanadium-4 tetrahedra. If we think about the ligand field splitting of a vanadium-4 center, that E set, that E manifold of orbitals, doubly degenerate orbitals, are not very stabilized relative to the kind of unsplit case, and therefore that's a poor hopping site for an electron. And so that led us to hypothesize that structures that are more corrugated and that have these vanadium oxide tetrahedra would lead to more localized electronic behavior. To probe that electronic behavior, we use diffuse reflectance spectroscopy. If you're not familiar with this, this is very similar to solution state spectroscopy, absorption spectroscopy, except that because there's a scattering coefficient, this is pseudoabsorbance, which is, in other words, the absorbance divided by that scattering coefficient. As a reminder, V2O5, vanadium pentoxide, is a wide bandgap semiconductor, and its band structure is comprised of filled oxygen 2p states, and its conduction band is vanadium 3DXY, empty states, antibonding also with oxygen 2p. So this band edge at about 2.3 eV represents transitions from the valence to conduction band. When we reduce vanadium oxide and then intercalate protons for charge balance, we now see a new big broad feature in the visible in IR, and indeed this compound is now black. This new feature is associated with, many view it as a polaronic peak. In other words, an electron can couple with vibrations in the lattice or distortions within a lattice. I often imagine maybe a ball in a rubber sheet. You can think of that as the dip in the sheet moving together with the ball as one quasiparticle. But to move that ball or that electron out of that distorted and energetically stabilized site to an undistorted site, there is an activation barrier, and hence we would expect a peak in our optical spectrum. Molecular chemists are perhaps more used to thinking about intervalence charge transfer. Here also there would be an activated process to hop between these metal centers as a function of what they're bridged by. And so in either case, and here we're not necessarily differentiating, though we tend to favor the polaronic case because we have this extended lattice, and metal oxides are known to have distortions of those lattices, coupling of those vibrations to electronic species. Nevertheless, though, these compounds are not metallic. In other words, they're semiconducting, and we do, from variable temperature conductivity measurements, see there is indeed an activation energy associated with movement of those electrons. Interestingly, then, our hypothesis was in our hybrids with more vanadium oxide tetrahedra, in the cases where we have hydrogen bonding and high charge density from our molecular species, we would expect a more localized behavior, and we do indeed see that. So now we see new, generally three peaks, slightly lower in energy than our valence band to conduction band transition for V2O5. And actually, an inorganic molecular chemist would look at that and say that looks very much like a vanadyl ion, even a vanadyl ion in solution. And indeed, those are just D to D transitions, connoting the fact that these are a very localized electronic behaviors. On the other hand, in cases where we have very regular layers with no vanadium oxide tetrahedra, such as those templated by ethyl viologen, we get a much higher electrical conductivity. I will mention these are I would say a lower bound on the conductivity because of these are measured with pressed powder pellets. So the intrinsic conductivity is likely higher. And we now see a big, broad absorption feature in the visible and near IR. And we believe that's because the peak of that polaronic activation energy is out of our spectral range. We have measured variable temperature conductivity and do see a much lower, though still present, activation energy there. But I want to make sure that everybody's noting this big, broad feature because that's very indicative of a significant degree of electron localization in hybrid bronzes, and it will come back in my high pressure story today. The downside of those vanadium oxide cases is that we have very little control over the degree of mixed valence. It's dictated by the reduction potential of the vanadium centers, its coordination geometry, and the molecular templation from the molecular species. But actually, in the molybdenum and tungsten cases, we have a bit more control. And that's because when we self-assemble these materials into these layered architectures, they are first synthesized with the metals in their fully oxidized 6+ oxidation state. And the molybdenum and tungsten are isostructural, so we can swap out molybdenum and tungsten at those metal sites. But the interesting thing is that our metal oxide layers are neutral and now have a bond, a coordination bond, to this heteroaromatic nitrogen atom from our organic species, but our organic molecules are neutral as well. And so there's no charge balancing requirement for their incorporation, nor have we sort of decomposed some of them to reduce the metal oxides and then protonated others. And so this gives rise also to a lot of interaction between these molecular species and the metal centers that we became very intrigued by also to probe, and that will be the basis of my high pressure story today. And as you might imagine, this allows us a lot of synthetic control as well. So here's an example where we can pillar between these metal oxide layers using 4,4' bipyridine, and that gives a very rigid pillared structure. But we can also incorporate monotopic ligands like pyridine, which now only bind to one metal oxide layer. Here now these layers are held together by much weaker van der Waals type interactions. We can also even cause an extreme canting of our metal oxide octahedra using these ditopic 1,2,4 triazole molecules. And you could imagine actually that this tilting of these octahedra should substantially change orbital overlap in these compounds, changing their band structure. But the really nice thing is that either before, during, or after their synthesis, we can reduce them either chemically or electrochemically, giving rise to our hybrid bronze. And we can do that, we can control the stoichiometry of how much reductant we add, and therefore control a wide range of mixed valence. So here is just to show that Raoul and Lachna, who really kind of did a Herculean effort here, put together this table of 10 different ligands two different metals synthesized through multiple synthesis methods, as well as multiple methods of reduction, and in many cases isolated many different types of or levels of reduction. And so this was a huge matrix of work because for each of these compounds, then they characterized the structural and vibrational and electronic properties of each of those solids. In this case, in both the molybdenum and tungsten UV-Vis plots, we can see that going from what's in light are the traces for the fully oxidized compounds, and then in the dark colors are the reduced mixed valence hybrid bronzes. In all cases of the hybrid bronzes, we now see this big broad absorption feature over visible and IR wavelengths, indicative of those relatively delocalized electrons. And so in all of these cases, we can control the level of reduction. And actually, that broad feature does scale with that level of reduction. We can develop nice scaling relationships of it, though you can see that the underlying electronic structure is more or less retained. And finally, what I'll just say is that going to a dimensionally reduced structure in this hybrid system, what we wouldn't want to lose are the electronic properties and capabilities of the parent inorganic solids, but actually comparing the conductivity of our hybrid system at a similar level of reduction, so a similar X value, to the inorganic hydrogen molybdenum bronze, our hybrids are actually more conductive. And so we're working on parsing out why that is. We can even tune things from the inorganic standpoint. So Anton, this is probably right after he got this result, he got single crystal structures that are solid solutions where we have a mixture of molybdenum and tungsten at all of our metal sites, a statistical distribution with no apparent ordering. And he's able to refine the relative ratio or the ratios of molybdenum and tungsten here. And what's gratifying is that those single crystal ratios match perfectly with our bulk elemental analysis if we synthesize this on gram scale. But the very interesting thing is that allows us to even tune the band structure here by about 200 MeV, changing the band gap, going to the mixed metal case relative to the single metal cases. And I have some arguments about why we think that is, which I'm happy to talk about in maybe the question and answer section. Okay, so I know that was a relatively protracted discussion of hybrid bronzes as an introduction, but since they're relatively new compounds, I wanted to make sure that everybody was on the same page. So now, taking a step back, because we want to develop the structure property and composition relationship understanding for hybrid bronzes, I think as I don't have to introduce any further, high pressure is a really great way to understand those relationships. And in general, high pressure, as we know, can induce many different chemical reactions and phase transitions, both structural and magnetic and electronic. And I think we especially appreciate that we are modulating the structure mechanically, but that can certainly track quite well with a lot of that chemical control that I introduced earlier in my talk. So especially because we can play with the rigidity of our metal oxide layers, as well as the tilting of the metal oxygen octahedra, we began by exploring the 4,4' bipyridine templated molybdenum oxide in its fully oxidized state. So here I'm showing in its powder form that light yellow or even close to white compound. In this case, this pressure medium is a soft alkali halide, KBr, but we've tried many different pressure media as well, and its behavior is very similar. Here's our ruby for our ruby fluorescence measurement. And what we were very intrigued by is then at roughly 13 gigapascals, we see an intense color change from this light yellow color to an opaque dark black. Raman spectroscopy, of course, is informative in that low pressure phase because we see shifting of our metal oxygen modes towards higher Raman shift, indicating that our lattice is becoming stiffer. But at least in our case, we were not able to collect enough light out once our sample became highly absorbing of light in order to see peaks. And so it looks as if the material is, of course, destroyed, though ex situ Raman and other measurements, of course, show that it is not. So that really just helps to pinpoint where that phase transition is occurring, but didn't really inform us much further from that. However, when we were able to secure beam time at both the advanced photon source and the advanced light source, and actually, this was my students' very first experiments at beam time, and we saw some very unexpected behavior. This lowest angle peak at just above 2 degrees 2 theta with this 25 keV radiation. And here, by the way, this is using a KBr pressure medium where I have an asterisk showing both the low pressure and high pressure phase of that alkali halide. I assure you it's much softer than our metal oxides. But again, we have also parsed out the behavior under other pressure media. So we track this especially lowest angle peak because it's the 001 reflection associated with the interlayer spacing between our metal oxide layers. And as one might expect, that shifts towards higher 2 theta, in other words, a decreased interlayer spacing with increasing pressure up to about 13 gigapascals. But upon the conversion of our material to this dark opaque black, we then see that peak, as well as others that are simply just not as visible here because I've put these patterns kind of squashed together in a waterfall plot. We see shifting back towards lower 2 theta. In other words, shifting, for instance, of that interlayer spacing towards a higher interlayer distance. That's obviously very unexpected. And our first instinct, of course, was perhaps maybe our gasket was failing or something else like that. That's not necessarily what one would usually expect to see. However, we reproduced this many, many times. And Lebesgue refinement of our data actually shows something even more unexpected. So here our C-axis, which of course is indicated quite well by that 001 reflection, but this is now from fitting all of the peaks with any kind of a C component. We see that it does decrease with increasing pressure up to about 13 gigapascals, but then proceeds to increase again all the way up to about 35 gigapascals, after which point it plateaus. Meanwhile, our A and B lattice parameters in this layered structure, so the directions that are parallel to our metal oxide sheets, actually become relatively invariant above that threshold pressure around 13 gigapascals. And so because they're invariant and our interlayer spacing is increasing, actually our apparent volume, our crystallographic volume, is increasing as well over quite a large range. And so that we would call negative volume compressibility. I'm sure many here on this call are familiar with the concept of negative compressibility. Typically, it's negative linear compressibility, in which case along one direction expansion occurs and contraction occurs along the other two to counterbalance it, or negative area compressibility, where expansion occurs in two directions and contraction in the third. Negative volume compressibility is actually thermodynamically forbidden, as I think many know. But the important caveat to that is it's thermodynamically forbidden in the elastic regime. So if we are in the plastic regime, perhaps with bond breaking or making forming or with phase transitions occurring, it is not necessarily forbidden. We are putting PV work, thermodynamic work into the system. And of course, then either if we are in the elastic regime, the system volume must decrease, or in the plastic regime, something must counterbalance that energy input. And so knowing that, for example, even pyridine and benzene under high pressure have been reported to form bonds, so de-aromatizing these molecules and even forming sp3 hybridized nanothreads, for example, we hypothesize that perhaps what could be going on is some type of bond breaking and remaking here, or phase transition, which could give rise to what is, at least from the crystallographic, so what we can observe from our diffraction peaks, what appears to be negative volume compressibility. Indeed, we carried out fits of our A, B, and C lattice parameters and calculated the compressibilities here just to confirm that the C lattice parameter does indeed show appreciable negative compressibility, and there is negative volumetric compressibility as well. So that's just fitting the data above that pressure threshold. Zooming in on the negative compressibility perpendicular to the layers, since that's the most severe effect, I'm now normalizing everything to the interlayer spacing at ambient pressure. And you can see that we actually even return to close to that original interlayer spacing at high pressure. Further, what's quite interesting is this is an irreversible phenomenon. So once we relax this framework, it reverts back to and even shows a slight expansion. And I'll show that in a moment. But since this is an irreversible phenomenon, which again matches quite well with our hypothesis that this is a plastic behavior, we hypothesize that we could perhaps use chemistry to try to interrupt this mechanism. Perhaps as a function of protons or electrons or both being present, we could interrupt a bond formation mechanism between our for instance, bipyridine molecules. And indeed, in the case of the hydrogen molybdenum bronze, the hybrid bronze, we do see a kink at around 13 gigapascals, but that material does not show an increase in its interlayer spacing at higher pressure. And so I think this goes to show that while we're not fully certain why this is yet, something is being interrupted. The tungsten compounds do show very similar behavior, though perhaps to a smaller degree, a more muted behavior. So the fully oxidized compound shows an increase in its interlayer spacing, whereas the hybrid bronze, the mixed valence compound, does not. And I assure you that this is not a medium-based behavior. So there are examples where negative compressibility is observed, where the system volume is reduced because a medium intercalates or inserts inside of a crystalline compound, but where then the crystallographic peaks would then appear as though the material is expanding. We see this expansion, the shifting of these 001 peaks, for example, to lower 2 theta at higher pressure, even in the absence of a pressure medium, though, of course, here things are broadened a little bit because of that higher degree of stress distribution in our without a pressure medium. We can also remove the rigidity of our structure to further test the hypothesis that it is important. And so here, taking away that pillaring and instead using the pyridine templated structure, which you might imagine has the ability to either interdigitate these pyridine molecules or have them tilt out of the way, essentially more degrees of freedom. As one might expect, we see a monotonic decrease in the interlayer spacing with increasing pressure. So essentially, the more rigid structure then kind of leaves fewer avenues for that relaxation of the structure as a function of the PV work that is being done on the system. And as I mentioned, this is an irreversible phenomenon. And so here are powder X-ray diffraction patterns comparing the pattern before and after this behavior. We do see retention of a lot of the crystalline peaks that are associated with the metal oxide layers, but actually those lowest angle peaks revert to even larger interlayer spacings once we've released this pressure, helping to show that this is a phenomenon that irreversible plastic behavior has occurred. I think as many of you are aware, unfortunately, though this is irreversible and that gives us a chance of characterizing what's going on, diamond anvil cells use, I believe it's nanograms of sample, so very little sample with which to do post-compression characterization. Luckily, working with Dr. Bianca Burl and later Matt Tucker as well for some analysis, we used the Paris Edinburgh cells at Oak Ridge National Lab to acquire milligrams of our sample, where here again you can see compressing our sample from this yellow color to this dark opaque black. Together with Bianca and Matt, we took a look at the neutron total scattering, in other words, neutron PDF. For those of you who are not familiar, these plots are simply histograms of interatomic distances in our lattice, where any peak you see is typically on the short length scale a bond, such as a carbon-carbon or carbon-nitrogen bond or a metal-oxygen bond, and at longer length scales that represents the periodicity of the lattice. Shown on the right here, at the short length scale, we can see that after compression, we actually don't see much of a change in the local coordination of our carbon-carbon bonds or of our metal-oxygen coordination geometry. But moving out towards higher or longer distances, we do see a reduction in the overall intensity and sharpness of these peaks, indicating that there's likely some disorder or partial amorphization within our structure. And so this is kind of our cartoony picture of what we believe is going on with respect to the metal oxide layer, where we have some regions that are of higher crystallinity and higher order, and other regions that are more disordered. Interestingly, and kind of supporting that, when we take that post-compression compound and mildly anneal it in an air-free, under air-free conditions at 100, 150, and 200 degrees Celsius after that compression, we see a return of many of these crystalline peaks. So we believe this is sort of a kinetic phenomenon where we've just trapped some of that disorder, and it's not necessarily a breaking of bonds within the structure. And so we're able to retain or sort of recover some of that crystallinity in the structure. So that's showing kind of what's going on with the metal oxide layers, but it still doesn't explain why we see this interlayer spacing increase and perhaps what's driving that disordering. And so there the clues came from mass spectrometry. On the top here, I'm showing 2 plots of liquid chromatography mass spectrometry, and on the bottom, I'm showing matrix-assisted laser desorption ionization mass spectrometry. For those who are not familiar, you blast your compound with a laser and see what particles or what ions come off. In both cases, we're running in positive ion mode. So a molecular unit is protonated by 1, and therefore, for example, bipyridine's mass is 156, but we protonate by 1, so its mass to charge ratio is 157. And in both our pre and post compression compound, of course, we see plenty bipyridine. But in only our post-compression compound, shown in orange in all of these plots, we see a large peak at a new retention time with a mass of 311, or a mass to charge ratio. A dimer of two 156 atomic mass unit bipyridine molecules should give a mass of 312. And if we protonate by one, that should have a mass to charge ratio of 313. So seeing this peak, which has a mass to charge ratio of 311, indicates that we've actually lost two hydrogen atoms. Similarly, here's at 156, we do indeed see our peak in both the pre and post compression sample and our MALDI. But again, we see a dimer separated only by 154 mass to charge ratio, not 156. And we even see the evidence of a trimer forming, which we believe doesn't show up in the liquid chromatography mass spec if it's stuck on the column as a larger molecule. So the interesting bit here is that's different behavior than, for example, I mentioned pyridine and benzene and other molecular species are known to form bonds and form sp3 hybridized oligomers or dimers as a function of pressure, but that does not involve any hydrogen loss. We did test molecular bipyridine. Here we do see a tiny amount of our dimer that has lost two hydrogen atoms, but by far the most of it is these oligomers that are separated by 156. In other words, those sp3 hybridized, perhaps if you want to call them, carbon nanothreads. So in other words, having the hybrid architecture in our metal oxide layers present gives rise to this unique, or at least much favors this formation of a dimer that has also then undergone dehydrogenation. That's corroborated by our solid state NMR. So here on the bottom, I'm showing pre-compression in the aromatic region. And of course, we see no evidence of any aliphatic peaks. And I've assigned, based on these color codings, these different aromatic or sp2 hybridized carbons. After compression, we now see new features in these spectra, and we assign those as bond formation between these alpha carbons and one of these two beta positions. If you were to digest these, the material, then actually whether you form this bond to this beta 1 or this beta 2, that's the same molecule, but of course in the solid state, that would be a unique bond formation. And we see no evidence of the formation of any aliphatic carbons. So the question then is, where do the hydrogen atoms go? In other words, where do the protons and electrons go? Well, we actually have a really nice proton and electron sink right nearby. In other words, the metal oxide layers can accept electrons. And here I'm showing XPS before and after compression, where after compression, we see evidence of molybdenum 5 instead of just molybdenum 6. UV-Vis also shows us this big broad absorption feature that we've associated all along as the presence of relatively delocalized electrons. And so essentially, you can think of this as in situ as a function of pressure forming some sort of hybrid bronze. And finally, EPR shows us a new signal, which we believe is electrons localized at distorted sites within the lattice. Actually, the hybrid bronzes in general tend to not show a signal in EPR, even though they do have unpaired electrons. And we believe that's because they're so delocalized and at high concentration that they quickly interact with each other and relax and are therefore not visible in EPR. Here, this signal matches quite well with electrons localized at defect sites in metal oxides, and many of those have been reported in the literature. And finally, to corroborate all of this, Theta Chen collaborated with us, so he's a professor at Notre Dame as well, and we attempted to simulate pressure. I would view this as very qualitative, which I think, predicting structure as a function of pressure is very challenging, especially with a low symmetry structure like this that has many atoms in a unit cell. But what it does show is this tilting of these bipyridine molecules as we begin to compress. And then at much higher pressure, I've highlighted here with this blue blob the apparent electron density in the system, where we do appear to start to see that this proton on this bipyridine carbon starts to have some shared electron density with oxygens that are bridging within the metal oxide layer, suggesting perhaps that the mechanism is assisted by that proton and electron hopping to the metal oxide layer. So our hypothesis is this, that as a function of pressure, we form a carbon-carbon bond between these bipyridine molecules. But because we've now formed a bond that is an sp2 hybridized carbon-carbon bond, the preferred angle between those bonds should be 120 degrees. In other words, we should then create strain in our system, which locally can force apart the layers. And as long as enough of those bond formations occur, crystallographically, it can appear as if our metal oxide layers expand, even if locally there's some disorder in the metal oxide layer or even within the organic layer itself. And further, we believe that process is aided by then the migration of these electrons and protons to the metal oxide layers. So we're really excited to continue pursuing that mechanism with a lot more high pressure measurements, especially in situ ones to track this mechanism. But I hope I've been able to show you that hybrid bronzes, we believe, have a lot of unexplored territory, both in terms of their elucidation of structure and electronic property relationships, but also especially under pressure, I think we can learn a lot. We're really excited to begin incorporating molecular species that can accept or donate charge as a function of different stimuli. And finally, ultimately, hopefully, we can utilize all of this information to develop design principles for energy-related applications. With that, I'd just like to thank you for your attention, and I'd be happy to take any questions.
Thanks very much, Adam, for a beautiful talk. This is really clearly a new area of chemistry. The synthesis of hybrid materials looks very rich, and then applying this under pressure and looking at new phenomena that emerge is very exciting. So thank you very much for that.
Thank you.
The talk is now open for questions and comments. There's already a question in the chat. Skylar, do you want to ask?
Yeah, so very beautiful talk. So basically, before we intercalated any molecules, there is protons already. I would like to ask, is these protons diffusible?
That's a really great question. Um, so, sorry, I'm getting echo. So there has been quite a lot of nice work back, especially in the 80s and 90s, on hydrogen molybdenum bronzes and looking at movement of protons within those, which I view as very analogous to our structures. And so that's people like Stefan Adams and actually Roald Hoffman and many others. And so both some impedance spectroscopy data as well as proton NMR data do appear to show that there is some mobility of protons, that there is actually quite a bit of ordering there as well, which caused some argument in the literature. People saw evidence of what they believed was at first was charge density wave behavior, and it turned out that it's more likely this proton clustering. So we do believe there is some mobility of that. We have yet to really fully parse that out, I think, because most of our conductivity measurements and impedance measurements we've been doing in pressed powder pellets and haven't necessarily always deconvoluted those. But we do appear to see some proton movement in our impedance measurements if we use blocking electrodes. And so I think the short answer is yes, there is likely some proton movement as well. But as I think many of us are aware, really fully parsing out where protons are and how they're behaving is a real challenge. And so we're still working on that too.
Okay, thank you very much.
Thanks. Okay, Roma.
Hi, really awesome work. You've done a lot of experiments. I can't imagine how much work this has been. I guess I was curious to know which of all the techniques that you used was the hardest to do in a diamond amble cell.
Oh, wow. That's a really great question. For these studies, I would actually say that none of the work we did in diamond anvil cells turned out to be all that challenging, because the only measurements that we did in diamond anvil cells were Raman spectroscopy, which we tend to do in-house, and I think a lot of folks here might do the same, as well as our diffraction measurements. So those were a little more challenging, but not too bad, powder X-ray diffraction. The rest of them may be kind of aided by the fact that this is an irreversible phenomenon. It was quite challenging to kind of get the Paris-Edinburgh cell measurements going at Oak Ridge National Lab. But then afterwards, then you just kind of have your sample and it's not in a pressure cell. And so then you quote unquote do a normal measurement, though of course you're really worried because you have very little precious sample. But we're really excited to move forward and do things like measure high pressure conductivity as a function, in these materials, which we would certainly do in a diamond anvil cell, but which would be challenging, though we have some experience with that. And also high pressure absorption spectroscopy to look at how do optical behaviors change in situ. And even we're pretty excited to think about doing even things like I have a student in my group who's working on doing in situ transient absorption, so time resolved measurements as well. So I think all of those will end up being a lot more challenging as well.
Very cool. Awesome work. Thanks so much.
Thanks.
Thank you. Christoph.
Thank you. Thank you very much for this very interesting lecture. Can I be a little bit provocative?
Yes, please.
Well, I'm not a great fan of representation of inorganic part of crystal structures by polyhedral representation. It's very misleading. What you really have in your crystal structures are nuclei and electron density. And you do not have an empty space in between the molecules. You still have some amount of electron density in the structure. Why not to study directly changes of electron density as a function of pressure in the case of your hybrid systems? It's possible. I mean, when I was younger, I studied plenty of similar systems. They do crystallize pretty well. You can get high resolution data even using diamond anvil cells. You can put a few crystals inside and get high resolution data and feed more flexible model of electron density against X-ray data. And then you can quantitatively trace what's going on with electron density. In fact, it's being transferred. It's being transferred between ions, among others. So your changes of colors are due to such charge transfer. Your negative compressibility is also because of exchange of electron density between atoms in the crystal lattice. We observe this very often in our high pressure studies. Also, you can see position of hydrogen atoms even in the neighborhood of very heavy atoms, as this is the case in your system. Additionally, it's not enough to concentrate on Bragg diffraction, on Bragg peaks. You went to Matt Tucker and I mean to ORNL to get powder data and used per distribution function. Why didn't you model this per distribution function with reverse Monte Carlo method just to get more structural information out of your data? Matt Tucker is co-author of an excellent software called RMC Profile, and a new version has just appeared. And you can use this tool and get better illustration of the changes you are getting in your structure. Additionally, this reverse Monte Carlo modeling can incorporate many different types of information into your refinement of structure, which is not done with routine crystallography. So you can improve your data in many respects, in my opinion. Please comment on the points I have just raised.
Well, thank you for all of those really great points, and I wholeheartedly agree with them. And so let me try to go through them, but if I miss any, please let me know. So maybe I'll go in reverse order. First, this story is by no means over. I would say this is sort of a major chapter, or we've maybe finished a first chapter. This is absolutely ongoing work, and I wholeheartedly agree that here clearly there is a lot of behavior occurring that is not necessarily ordered over the long range. And so analysis of that paradistribution, that total scattering, is going to be hugely important. And we're continuing to work with Matt on doing just that. And I agree, using something like RMC profile would be wonderful. We are working on it, though it's been exceedingly challenging, partially because relative to some of he actually just had a really nice paper come out with actually the Kurunadasa group and others looking at, I believe it's a cesium-lead halide as a function of pressure with sort of these larger box modeling and reverse Monte Carlo modeling. And so I think the challenge for us here is that we have way more atoms in our unit cell here, and kind of a lower symmetry, so way more going on. So that modeling is just going to be more challenging, but we are absolutely working on it and hope to do so better. We are also actively working on a whole host of different neutron measurements to hopefully get better contrast. And here our system is actually quite relatively easy to deuterate. So hopefully we can get information both from diffraction, but also total scattering, as well as inelastic scattering in neutron measurements to look at the role and location of protons, especially in situ in a Paris-Edinburgh cell. And I would also say we would love to do, for instance, single crystal measurements as a function of pressure rather than powder. I think it has been a challenge so far, and to a certain degree, we did our best to do a lot of different techniques, but we would love to do that and can work on that. There is a silver source diffractometer here at Notre Dame that we can try to use, or to try to do.
Go to synchrotron. I mean, you will not get the quality you need from laboratory diffractometers. Go to synchrotron, go to APS, go to ESRF to get decent data from the best stations.
I completely agree. And so, we would want to get high quality data for that. And I think the reason, and hopefully maybe this was the first point, was that you took some issue with, how these structures are represented. We try to show them with these polyhedra simply to help represent the coordination geometry and connectivity. Though I completely agree, of course, these are not space-filling models and not really truly showing where the electron density is, especially if there are these kind of less periodic phenomena or active bond formations occurring. And so if we were able to do that modeling and really get sufficient quality data to do that, I think that would be a wonderful insight. And so I would love to maybe pick your brain further in the future about how best to do that. We've done our best with what we can, but I think I will just again say this is by no means a complete story. And my students are continuing to work on this to the best of their ability. I think I covered all of your questions, but please let me know if I didn't.
You have answered. Thank you very much. Thank you.
Thank you.
Yeah, thanks very much. I'd like to jump in. I have a similar comment, but a slightly different take. Maybe it's simpler. And that is, if you suggest there's a violation of thermodynamic stability, you don't need to invoke plasticity as the source of it. Assuming you have equilibrium, thermodynamic stability applies whether you're looking at the bulk or the lattice, right? So it's really the bulk effect. So you are measuring in your Bragg diffraction the diffraction from the heavy atom lattice, right? And you don't see a lot of the structure. Maybe you see a little bit in the PDF and the non-Bragg diffraction. We see this all the time. We've seen it many times when you have two phases. You have amorphization, you mentioned amorphization, and you have two components. So you can see the expansion of the ordered component, but you're ignorant of the non-diffracting or invisible component. And in fact, that is compressing faster. So the bulk volume is decreasing. There's no violation of thermodynamic stability.
Right. I wholeheartedly, I completely agree. And I think perhaps I should have kind of said that more as another potential explanation. Yeah, absolutely. I think I just wanted to make sure it was clear that technically even negative volumetric compressibility is not technically thermodynamically forbidden, but obviously, yes, that is very much and probably the explanation I would favor that we have some regions that are currently at least more invisible to us, that are more amorphous, more disordered, and those themselves could then accommodate that volume reduction, whereas then other areas at least appear crystallographically to expand, though of course it doesn't mean, of course, that our overall system is expanding. Yes,
Right. And the
yeah.
easiest way to check that, and the way we always checked it, was just by doing microscopy of the recovered sample, and you can see the two phases present. So
Yeah,
microscopy would be the other thing, whether it's just optical or TEM or some other kind of microscopy, but that's a good check on that.
Yeah, we really want to do that. And we've looked and can't really see evidence of multiple phases there. And the weird thing, that this is maybe a little, the sample doing a little eyebrow waggle at us or something like that. In a lot of cases, both when without a pressure medium, but even with a pressure medium, it does appear to expand. But of course, that could be many different things going on. I think it would be really neat to even try to do some sort of tomography or something where, or something where we could look at actual domains, maybe through an in situ technique, to see if possibly at least some domains are expanding, or whether nothing is actually physically expanding, but it just looks that way crystallographically. Yeah.
Right.
So I completely agree.
Yeah, thanks. Okay, more comments, questions?
If I could ask, I mean, if I could present a short comment, you also have electron diffraction, which could be very useful, especially to trace where those hydrogens are, because these systems should be really excellent for electron diffraction studies, and so please try to get structures from electron diffraction data.
I think that would be really great, and we will try. I promise we will. We've had some trouble so far in the few electron diffraction measurements or electron microscopy measurements we've done so far of a little bit of our samples overall tend to be decently stable, so not as unstable as, for example, some other organic inorganic hybrid materials under the beam. One of our worries, though, is that the beam itself is perturbative there. But I think there are ways around that, certainly by tuning the beam and yeah, different sort of like measurement parameters that we should be able to get more data from that. And so yeah, maybe a micro ED type measurement or something like that.
Yes,
would be
exactly. Yeah. Thank you.
Okay, if there are no more questions, let's thank Adam for a great talk.
Thank you.
And we look forward to staying in touch.
All right. Well, thanks, everybody.
Yeah, thank you for joining us.
I guess I'm happy to stick around in case anybody has any final questions, but I know
Abdul does. No?
Oh.
Right, that's just a clap.
Oh, that's just a clap. Thanks.
Okay.
and thank you once again. I'm really honored to be able to deliver a seminar. So thanks for the invitation.
Yeah. Okay. Well, come and visit. You're nearby.
I'd love to. Likewise. Well, I know you were just here, so maybe, yeah, I'll try to make a trip out there. Yeah.
Great.
We still, I just comment, we still uses his slide from the summer school to give it to new students.
Oh, very cool. Yeah.
Yeah. I think you maybe remember those slides where you give like very basic introduction of DAC.
Oh, wonderful. Okay, I'm glad that's
we still uses those things.
Yeah, that's right.
Oh, fun.
Yeah.
Okay.
Cool.
Well, I'm sure you would have a lot to add to that. So anyway, okay. All right. Take care, everybody.
Okay. Thank you very much. Bye-bye.